Hello all. In this video, we are going to learn about ideal transformer on no load. So this is a core type transformer and here is the primary winding at which we are going to connect the supply voltage. Okay, so this is the primary winding. So let us consider this primary voltage as V1. Okay, so, and other side we will be having another winding that is called the secondary winding. Usually we will be connecting load. But in this case we have not considered the load because we are going to discuss the condition called no load. Okay. So after connecting the supply voltage, the transformer will take very little amount of current that is called the no load current I0. Okay, so this is an alternating current and this winding is a conducting material and all. So, and after that, this current will produce a flux in the primary winding. That flux is called the main flux phi. Because of the of this flux, another an EMF will be produced in the primary winding. Let us call this as E1. Okay, so this flux is going to link up with the secondary winding through the core like this. Okay, so this is the flux direction. And again, according to Faraday's laws of electromagnetic induction, you may observe one more EMF here. Let us call that as secondary induced EMF E2. Because there is no load, current is zero. That means I2 is going to be zero, but is not the terminal voltage. Okay, so you may equate this to V2 also, where V2 is the terminal voltage or load voltage. Okay, so before getting into the phasor diagram and all in detail, okay, so we have to note certain points. As we have considered the ideal transformer, the winding resistance is zero. So both in primary as well as in secondary windings, the winding will have zero resistance. Like that we need to assume. So that means both the primary and secondary windings, they behave like purely inductive in nature. So because of this reason, so this current lags the supply voltage V1. But before getting into that, let me tell you this no load current I0 will have actually two components. One is called the magnetizing component of current, other one is called the working component of current. This magnetizing component of current is the component which is the reason for the magnetization of the core. Okay, so second one is a working component. This is the component of current which is responsible for the losses in the transformer. To in order to serve the loss, again it needs some component of current. So that component will be considered as working component of current. As we have considered ideal transformer, so we may say that the ideal transformer as loss free also. So that is the reason why this working component of current is absent in the case of no load, ideal transformer on no load. So we will be having only magnetizing component of current. That means this I0 that is called no load current is nothing but your magnetizing component of current. As we have considered ideal transformer, both primary and secondary windings will behave like inductors, purely inductive in nature. Okay, so this magnetizing component of current is very little because you don't have any load on the secondary side. So this component of current IMU is very small in magnitude and it will lag the supply voltage V1 by 90 degrees. Clear? So uh, as I said, okay, so the windings will behave like inductors, okay, purely inductive in nature, so it will lag by 90. So this is one point you need to remember. And then what happens? This magnetizing component of current I mu will produce the flux phi. Okay, so that means this flux as well as the magnetizing component of current should be placed as in phase with each other in the phasor diagram. Okay, so the flux phi and the magnetizing component of current, they were in phase. Okay, so next, because of this flux, what happens? EMF got induced in the primary winding, that is called E1. Okay, so here we need to underline one law called Lenz's law. According to Lenz's law, okay, so this EMF will oppose the cause. Here the cause is nothing but the supply voltage. So this E1 will be in anti-phase with the supply voltage V1. Okay, so and also if we consider the secondary induced EMF E2, so this will also be in anti-phase with the supply voltage according to Lenz's law. So on that node, E1 as well as E2, both the EMFs will be in anti-phase with the supply voltage. So in the other way, what we can say, both these EMFs should be represented in phase. Then only both the EMFs will be in anti-phase with the supply voltage V1. Okay, so these are the points you need to remember. Okay, so let us go with the phasor diagram with inclusion of all this explanation. So as the flux is common for both primary and secondary windings, you have to take flux as your reference. Okay, right. Now, what happens? The first point, this I mu, magnetizing component of current, will lag the voltage V1 by 90. So before that, we will include the second explanation that we have discussed a bit back. Okay, so this magnetizing component of current and the flux, they should be in phase. Okay, so let me pick up a different color um, to represent current. Okay, magnetizing. So let us consider this current as magnetizing component of current, which is also called as no load current as of now. Okay, because so how it got equal? Because it is an ideal transformer, you don't find any working component of current. Okay, right. So now let us include the first statement now. Okay, let me pick up another color. Okay, so this vector will be called as V1 because this I mu is lagging V1 by how much angle? 90. Okay, as this I mu is already mounted on x-axis, it has to lag. So obviously V1 need to be mounted on the positive y-axis. Okay, so here the angle is how much? 90 degrees. Right? So now if I consider the number of turns on the primary side as N1 and the number of turns on the secondary side as N2. Okay, so we will observe three conditions here. One is N1 equal to N2 or N1 greater than N2 or N2 less than N2. So there are three possible conditions. Based on that we can define different categories of transformer. Okay, if I consider the equality, that means if number of turns N1 is equal to number of turns N2 of the secondary winding. Okay, primary number of turns and secondary number of turns. So as we all know the transformation ratio K, so which is defined as K equal to N2 by N1. Let me start with number of turns only by N1, which is equal to E2 by E1, which is equal to V2 by V1, which is equal to I1 by I2. Okay, so let us pick up, so this condition only. That means N2 by N1 equal to E2 by E1. Okay, so by simple observation, we can say that number of turns are proportional to EMF or EMF is proportional to number of turns. Okay, so if I consider the equality condition, that means E2 equal to E1 will be the condition, or E1 equal to E2 will be the condition. And according to the third point, if you can observe here, E1, E2, they should be in antiphase with V1, and they should be, this E1, E2 should be in phase with each other. Okay, so let us represent those two vectors also in our phasor diagram. Okay, that will be represented with some other different color. Okay, so let us consider this as E1. Okay, as I have considered 1:1 transformer, or n1 equal to n2 in this condition, so I may equate this to E2 also. And one more point, I need to represent V2 also, right? So here also, here already represented as E2. Okay, so E2 is equal to V2, because there is no resistance in the winding, no current on the secondary side, so there won't be any drops. So E2 is simply is equal to V2. So you may also equate here with V2 also. Okay, so this is how you need to understand the ideal transformer on no load, and this is the corresponding phasor diagram. I hope you understand. Thank you so much for watching this video.